So force of gravity. Okay. So question: when we did case number one, did you all have the same inputs, givens, or different ones? Different ones, because each pair had what? Had different what? Had different masses and also had different what? Had different distances if you chose to. How about case number two? Was it also okay? For you, it was all the same what? The same numbers because we all did the moon and the what? And the earth, and they had the same distance. But in general, when you do celestial or astronomical bodies, do you always have the same numbers or three different numbers every time? Three different numbers every time because it depends on which two bodies you're doing and how far they are. How about the third case? Did all of you have the same numbers? Almost. What same numbers did you all use? For sure. You all use the same distance, which is the radius of the what? Radius of the Earth minus the 1 meter of half of your height. No one cares. The gravitational the gravitational constant, and also what? One more. The mass of the Earth. What was the only thing that all of you potentially had different? Your own mass. Exactly. So that means whenever you're interested in calculating what the force of gravitational attraction between the Earth and any object where on the surface, you will always use this equation. You already have the structure for it. You just have to fill the top and the bottom parts. All of you had the same capital G. All of you had the same mass of the Earth. You can call it capital M. No need. You can just subscript it. You all had, what is this? What does R mean in math? Always, especially for radius, because we all did not care about the half of the height. Radius of the Earth, don't forget to what? Square it. And then all of you potentially had a different what? Mass of your own body as the mass of the object. Okay? So if you really think about it, if all of us used three same numbers and differed only in one, can we just pull away those three numbers and always have them like, calculated and ready for use? What do you think? Would it save time for the next one? Yes. So that means what? We can definitely play with this. Which three numbers do I need to pull away? Like have always ready and done. Yes, Ali. Exactly. G and R Earth squared. So that means I most definitely, what's up? You will most definitely can write it like this. Collect it in a bracket, and then just what? Ditch the one that keeps changing on the other side. Basically, by the way, how many people see that this becomes a function? Raise your hand if you know what I'm talking about. What's a function? Everyone? Come on, we're physics people. All of you are doing 11 and 12. What's a function? Say again? So that means a function needs a different what every time? X value. What's an X value? Input. And it spits out a different what? Output. So that means what? Is this now a function? Yes, it is. What's the only input that will be different every single time? There you go. So technically, if you really want to put a function notation to this, you should put what? You should put FG. Don't do that, but you should put FG and then bracket. And what do you put in the bracket? Well, your x is the what? Is the mass of the object. That's basically it. All right, so this is a function. Okay, can we right now, do we have the three numbers in the bracket? Can we just do the calculation right now? Yes, we can. Okay, so this is your next slide now. Let's do the calculation step by step. All right, so let's go to the next slide. Okay, so here is the value. Go ahead, come on. The value of the bracketed expression, only the bracketed expression is G is 6.67 times 10 to the negative 11. Mass of the Earth to 3 sig figs is 5.98. And finally, the radius of the Earth in meters, 6.4 times 10 to the 6, or 6,400,000 meters to a power of 2. All right, can you do the splitting method with this? My splitting method. Yeah, of course. I mean, you can choose to. You can do this and this and this squared. Don't forget the square. And then you can do the power of 11, minus 11, the power of 24 over a power of what? 8 or 12? 12, because you shell inside a shell, you multiply. Or you can just clean up the top part and then clean the bottom part. Okay, so let's see which method I used. I think I used the cleaning up method, not the splitting one. Yes, I did. So I basically just multiplied all of this together. That gives me 3. I just kept more digits than necessary probably, but 3.9887 times 10 to the 14 divided by 4.096 times 10 to the 13. Okay, go ahead. I want you to plug this in. Go, go, go. Use your calculator or your cell phone. How many people got this answer? Raise your hand if you got it. Okay. Now, what is this number suspiciously very close to? 9.8. Did we get this by using an experiment or a theoretical calculation? Yeah, what numbers did we use? We used the G, we used the M, we used the R. What does radius mean? What's the only shape that has a radius? Circle, or in 3D, what do you call that? A ball or a sphere? Is the Earth. It has, but only in what? On the surface. Is the Earth a perfect sphere? No, it's not. No, it's not. Worse, does the Earth have perfect density? No way. When you go deeper into the Earth, what happens to the Earth? Same layers or different layers? Which means what? Is this theoretical calculation correct? Is it a good approximation? What is always correct, theory or experiment? Experiment, because it doesn't matter how beautiful your theory is, if the experiment doesn't prove it or doesn't confirm it, the universe does not bend to anyone. I don't care if you're Einstein. You need to perform what? An experiment and then prove it. So which one is more accurate? Because it was actually what? The experimental measured value. Is it making sense now? That's why. This was a good shot, right? It wasn't that bad. That wasn't that far off. But you need an experiment. Perfect. All right. You. Okay. So this simply means that if you're trying to what? Get the force of gravity on yourself, do you need to do this calculation every single time? No, because we've already isolated what? A bunch of them. Ladies and gentlemen, here is the FG equation, which I already covered with you very briefly. Very briefly, when we did the engineering forces last week, I told you, don't worry about why it looks like that. Trust me on it. We just proved it. We just proved that this reduces to what? This. Where, though? Only when you are on what? Only when you are on Earth. And where are you on Earth? On the surface, or what? Very close by, such that the 9.8 is still applicable. Like maybe above the surface of the school. But do you think above Mount Everest, would it be 9.8? If you drop a pencil from the top of Mount Everest and you measure its acceleration as you drop it, do you think it's going to go down to 9.8? Do you think it's going to go down at a higher than 9.8 or lower? Lower, because it's what? Because it's further from the core. It's pulled at a more strength or more weakness. You got it. Yes. Distance matters. Okay. I love this formula. It rhymes. Read it. Fg equals, done. Fg equals mg. One of the cornerstones of engineering and physics. Okay, Fg equals mg. This tells you that Fg is just the product of what? Mass, and what's g? That's it. If I ask Feynman right now, Feynman, what's the force of gravity on you? Do you need to do the big calculation, or you can just do that? You can just do that. But what number do you need about yourself? You need your mass in what unit? Pounds or kilos? Always kilos, and you just multiply by what? 9.8. Well, let's prove that. Does anyone remember my mass from yesterday? Because I did case number 3 with my. Go ahead. Multiply 64 by 9.8. Go. Multiply 64 by 9.8. Tell me what answer you get. Say again. 627. What did we get yesterday? Does anyone? I think we got on the video. Oh my God! I think we got 623. Okay. I want you to multiply what now? Multiply 64 not by 9.8. Multiply by the approximated value, the 9.73623. Do you see what I mean here? Why go through a big calculation when you have a shortcut? You have this thing called 9.8 ready to be used. It just needs what? It just needs what? Your mass in kilos, and you are done. All right? So True or false? Does this equation apply to the International Space Station? Why not? If I ask you for the weight of the International Space Station, does that equation apply to it? Or the force? No. Why not? Because it's very what? Does the 9.8 apply at that altitude? No, it doesn't. Done. You can't apply it. This is a special case. That one is the general case. By the way, this is similar to what? Does factoring always work? Does the quadratic formula always work? Yes. You see what I mean? That's it. One of them works all the time, but it just takes what to apply? It takes time, and you could make a mistake. How about the other one? If it applies, would that be good? Yes. Factoring, if it works, do it. Quadratic formula is the big gun. You just leave it when you need it. Okay? Or you just leave it to your last resort. Okay. So let's do. Go ahead. Isn't that just the G part of any planet? Look at it. Yes. How do you calculate the gravitational acceleration of any planet even before visiting the planet? You just need to know two things. Number one, you just need to know how much mass it has in kilos, and you need to know how much what radius it has in what? In meters. Okay? So let's do this together. What is the mass of the moon from yesterday? Does anyone remember from the notes? 1,000. How much? 1,735. So go ahead. Equals. Come on, where is it? Equals 6.67 times 10 to the negative 11. How much again? 7.35. Sorry. Sorry. What I said was the radius. So we need the mass first. Mass is 7.35. 7.35 times 10 to the 22. What was the radius? 1,735 what? Kilometers. I need to switch it to what? Meters. Well, if I multiply it by 1,000 and then write it in scientific notation, it will be, instead of 6.4 times 10 to the 6, it will be 1.735. Let's use all the digits. Times 10 to the 6. All what? To the power of? To the power of 2. Okay? Can you do the splitting method with this? Yeah, you can. You've got 3 numbers and 3 powers of 10. Just don't forget the square. I'll show you how. By the way, if you want my advice to how to do this in one shot using a single display without making a mistake, I'll show you how. Which part is the biggest part of this equation? Yes. Okay. Which part should we do first? Which part should we do first? Maybe the fraction. Yes. Oh, so let's do the fraction. Now, what good button to always use with powers of 10? What? EXP. So that means what? Look, everyone. 7.35. EXP what? Come on. 22. Divided by. I don't need this. Let's keep. Divided by. I'll put a bracket. Okay, what goes in the bracket? 1.735 x what? 6. Close your bracket. And then what? Square it. Equals that. Then what do I do with this number? Technically, I've done all of this part. Technically, right now, I finished all of this part. So what should I do now? What's missing? Multiply it by the 6.67. And don't forget, yesterday, some of you only multiplied by just what part of the number? 6.67. You forgot to multiply also by what? 10 to the. Remember, that's what brings gravitation down. That's why gravitation is the weakest. Not because of 6.7, because of 10 to the negative 11. So times 6.67 x, I have to go 11 and then put the minus. By the way, do you expect the gravity of the moon to be stronger than Earth, equal to Earth, or weaker? Weaker. All right. What was the one for the Earth? How much? How much is the number for the Earth? 9.8. Okay, let's see how weak it is. 1.6. What does that mean? You drop something on the moon, you just drop it. Does it travel as quickly or much slower? It's being only pulled down at an acceleration of 1.6 meters per second squared. What does the question say at the end, everyone? What do you think they always mean when they say compare? So this is 1.6 meters per second squared. Oh, question. Ali, when you did the 9.7, you put newtons after it, right? Yeah, I told you to what? Erase the newtons. It's actually not newtons. It's what? It's a meters per second squared. Okay, let's compare. What's 9.8 divided by 1.6? Yes, the gravity on the Earth is 6 times at least stronger than the what? Than the gravity on the moon. All right. You still have 2 more slides. I just want to do the first problem because the second problem is just asking you what's the gravity of Jupiter. Can you still do the same thing? But what do you need about Jupiter? You need its mass, and you also need its what? Radius, not diameter, radius. Okay, let's do this problem. I believe you guys have it here. PPT files, student. Yes, right here. Okay, Noura, can you read the problem about the 2 asteroids? What are they asking you for? How far must they be from each other to what? To have that much attraction between them. Question for you. Did they give you the diameter of the asteroid? So what kind of, okay, so do we really care about the size of the asteroid? No, we know they're big, but for some reason, they did not tell us the what? The diameters or the radiuses, sorry, radii of them. So my question is, whatever distance you get, would it still be center to center? Yes, everyone, always remember the distance you use or the distance you get out is always what? Center to center. Even if you're not given the centers, they just assume that the steroid is approximate as a very thick, dense dot. Okay, always center to center. All right, let's do this question. So let me just put Microsoft Paint up. Okay, what equation am I going to use? Still, am I going to use the small equation or the big equation? Why not small? Because they're both big, and is one of them stuck to the surface of the other? Potentially not. And that's why you never assume special, you assume what? General. All right, what's the equation? Fg equals what? G m1 times m2 over what? D squared. If you're a fan of doing symbolic manipulation and then plug in the numbers at the end, be my guest. If you're a fan of plugging numbers in now and then doing the manipulation, be my guest. Let's do the numbers. All right. What's the power? Sorry, I mean, what's the force of attraction between them? What is it given in the question? 2.2 billion newtons. All right. 2.2 times 10 to the 9 equal 6.67 times 10 to the negative 11 time. Okay, Noura, what's the mass of the first asteroid or second? Doesn't matter. So one of them is 10 to the 20, and the other? Oh, sorry. Uh, Oh, so also 10 to the 20? Oh, so one of them is just 3 times heavier. Don't say bigger. Say what? Because big includes, sorry, big, describes what? Mass or size? Please remember. Yes. D squared, do I know it or do I keep it as a symbol? Yeah, it's my variable, so I'll keep it as like x squared. No more physics. Math is takes over. Can someone tell me what math step I should do? Think easy and clean up. What should I do first? Yes, technically, there's an invisible what here? 1. So 1 times d squared is a d squared. So let's clean the top up. So 2.2 times 10 to the 9 equals something over d squared. I don't need calculators for this. Can we do this in our head? Yeah, we can. There's a lot of powers of 10. What's 20 plus 20? 40. Take away an 11. 29. Done. 29 times 10 to the 29. 3 times 1 times 6.6. Do you see how easy it is? So 20.01. How do I solve this for d squared? Come on. Yes. You what? You crisscross. Okay. What do I do now? This guy goes with this one. And this goes with this one. 2.2 times 10 to the 9 It's a good time to be a teacher. No, because now I know by hovering, like the four corners match up. Yep. Trust me, the first time I applied for Fonseca and I didn't, he's like, "You're so archaic. Just use the blackboard." I'm like, "I'm archaic." That hit hard. All right, 20.01 times 10 to the 29. What do I do now? I divide first, and then I what? Square root. Yes. So D in one shot is 20.01 times 10 to the 29, all dividing 2.2 times 10 to the 9. I am, because I need to get only the distance. That's it. All right, let's do this in one shot here. Okay, 20.01 x 29 divided 2.2 x 9. And then what do I do with this number? Square rooted, where is it? I think it's here. There we go. Let's write it in scientific notation right there. Boom. 3 point, can somebody read that? 3.01. 0.15 is it? So 0.2 times 10 to the, what was it? 10. In what unit? Meters between the centers. Can someone convert this to kilometers? How do you go from meters to kilometers? No. Oh, remember, when you go from a small unit to a big unit, you always what? Divide. When you go from big to small, you multiply and magnify. So this would be what? This would be, yes, 3.02 times 10 to the 7 kilometers. Hey, let's play with the power of 10. I don't like 7. I like a multiple of 3. What's the closest multiple of 3 to 7? 6. So let's steal a 6, which means here I have to remain with a what? With a 1. 3.02. Still in kilometers. I'm not doing scientific notation here. I'm just trying to give it a physical sense. So this is 30.2. Can someone tell me what's 10 to the 6? Million. They are 30.2 million kilometers apart. How far is it surface to surface? I need to be given the radius of each one, right? But everyone, look, everyone, sketch this. Go ahead. Big circle, small circle, assuming the lighter one is smaller in size. And what we got is from where to where? Center to center. I have no idea how much is it surface to surface. Well, they didn't give me information. Why should I ask for it? Done. Make sense?